Hi everyone and welcome to a session with Anselme Tueno. Today we're going to talk about integrating and evaluating quantum-safe TLS in database applications. We're going to have the opportunity to look at some of the quantum-safe algorithms that are out there and see how they can be applied to sort of an industry application setting. We're also going to see performance evaluations of these kinds of algorithms, so stay tuned for that. I think a good place to start this interview would be to talk a little bit about time horizons when it comes to the implementation of post-quantum cryptography in general. So that's very much the focus of this paper. And given that this is a, let's say, field that's progressing, we're having this discussion now in the, beginning of February 2024. Would you mind describing kind of where we're at in terms of adopting or implementing or regulatory frameworks around post-quantum cryptography at this point?
So first of all, I think that many big organizations are trying to assess the algorithms to get them into existing applications. There are some, I think, there are, for example, Google's who already did something like secure TLS or something like that using quantum safe schemes. But I'm not aware of someone who is using it already productively. One reason might be that people are waiting for the standardization of this to be completed. So the standardization is still ongoing.
Yeah.
There are drafts for standards for four algorithms that have been selected, and NIST is NIST 3 months ago. NIST was looking for public comment, and they will use those public comment to improve the drafts and probably make them public this year or next year, something like that. So when the standards are out, I think that people will start using them productively.
Do you know what the ambition is for, let's say, what protocols to release? So there are 4 candidates now, is what you're saying.
Yeah.
Among these 4, is the ambition to narrow that down to, let's say, 2 standards or something like that? Because I take it that it was plural, like that we're not
No,
looking for one standard necessarily at this point.
no. The 4 schemes that have been selected will all be standardized. So the standardization initially started with more than 80 schemes, and after 3 rounds, they selected 4 schemes. So 1 key encapsulation. This is for exchanging symmetric keys between two parties, and 3 schemes for digital signatures. So there is still a 4th round that is going on that will evaluate other algorithms, and so there will be different for each of the schemes. There will be a different standard document, but I think all will be in the same will be part of the same new standardization for post-quantum cryptography.
Okay. In addition to the 4 schemes that we have proposed now, we also have 5 families of post-quantum cryptographic algorithms, right? Could you quickly just give an overview of what those are, and then maybe how these 4 fit into those categories?
Yeah. Basically, as I said, there are 5 families. There are lattice-based, there are code-based, there are hash-based, isogenies, multivariate. Among the 4 schemes, I think the majority is lattice-based, and 1 scheme is so among the 4 schemes that have been selected already. The majority is so 3 of them are lattice-based, and 1 is hash-based signatures. So from the multivariate family isogeny, there is no scheme selected now. 2 of the schemes that were promising on those families have been broken during the standardization. So between the the one I think one of the scheme was broken before announcing the result of the third round, and another scheme a few months later. So so set all the four schemes belong to either lattice space or hash based signature. So three other schemes will be further analyzed in the fourth round, and those three belong to code base.
Okay. So can we maybe narrow down a little bit on the lattice-based ones, given that we have most of the participation from that category? My understanding of this is you have some grid-like structure or lattice structure, and then on that structure you somehow encode a problem that's difficult both for a classical algorithm but also then for a quantum computer to solve. Is there some commonality as to what kind of problem in the lattices these schemes usually employ? Like among these three, let's say, or even the wider category of schemes that are not selected, or is there generally one problem that we try to attempt solving with slight variations in these schemes, or are they very different?
Basically, they are based on the so-called short vector problem. So first of all, a lattice is like a grid, a multidimensional grid, and so basically you can see it at the intersection point between between the n-dimensional space and the grid. So the grid must not be necessarily orthogonal. And when you have this structure, you can define you can define problem like the short vector problem or the closest point, the closest vector problem, and most of the latest schemes relies on this problem to ensure their security. So basically, so some schemes use problem like learning with error, and it is shown that the learning with error problem is as difficult as those latest problem. Exactly.
Okay.
So it is a little bit the connections. Yeah.
Right. And for solving those problems, is there a way to, let's say, concisely describe how you do that? Like, can you paint some intuition, if possible, as to why that's also hard to solve both on a classical computer, but then also on a quantum computer? Those kind of problems.
So I think this is a very technical question. So I'm not much into this aspect. I will this is a very technical questions that I cannot answer right now.
That's fine. No, that's fine.
Yeah.
Okay. Given that we have one of the four candidates in the multivariate category, I think you said as well. Could you quickly just describe on a high level
in the latest one candidate is hash based.
Sorry. Yes. That's my bad.
So
in the hash based category,
there is no candidate on multivariate that has been selected. Yeah.
Right. So would you mind describing, so given that we have one in the hash-based category, would you mind describing that one just like briefly on a high level to paint some intuition for what those schemes are doing?
Hash-based means that so the assumption relies on basically cryptographic hash function. This is all you need to have those kind of digital signature. First of all, you can use hash-based only for signature. You cannot use them to do key exchange. And basically, what you do is, at the very simplest level, is you split, you represent your message in bits, and for each bit you select a random string. So then you can this random string is your private key, and you hash the random string and make it as public key.
Okay.
So so you do this computation for 0 or 1. So if your message has 3 bits, for example, for each bit, you choose two random string, one for 0, one for 1. And you hash them using a cryptographic hash function, and all those hash will be your public key. Now, to sign a message, you will just choose you will just choose the string corresponding to the bit at at that position, and this is the this is the signature, because everyone knows the public key, everyone knows the hash function. They can hash themselves and check whether they get the same public key. So this is the basic idea how those schemes are constructed.
Okay. Okay, cool.
Yeah,
So thank you for the overview. And now then to tie this a little bit to the paper as well. So this is for a TLS scheme in database applications in particular.
yeah,
Could you describe maybe how TLS fits into the picture of these cryptographic schemes? Like, what is the connection now? Because we have these algorithms, presumably
yeah.
that are hard to crack with a quantum computer, but it doesn't really tie that to any specific applications, if you will. So how do we now tie this into something like TLS for database applications?
Yeah. First of all, TLS is used to secure the communication between two parties on the internet. What does secure the communication mean? This means that we want to ensure that we are talking with the right party, and we want to ensure that no one in between can read the communication. So to do that, we need basically two things. We need to be able to authenticate the parties, and we do this using digital signature, a public key digital signature. So this means that there is the concept of public key infrastructure, and people can generate certificates, so-called certificates. The certificate is basically telling that this is me with my name, and this is my public key, and this information, and I'm using this algorithm and so on. And this information is certified by a so-called certificate authority. So this certificate can be made public, and everyone can use the public key to check whether something that has been signed with my private key is from me. So there is the so-called authentication. So we need to ensure that we are communicating with the correct parties, and there is the key exchange. So in the TLS, the server the client contact the server wanting to secure the communication, and the server will send a certificate to the client and sign some message in between that the client can verify to be sure that the message is coming from the server. In this process, they will also do a so-called key exchange or key encapsulation. So they will generate a common symmetric key that they will use after that to encrypt all the communication between them in that session. So this is a little bit how you put post quantum into TLS.
Well, is that really how you put post-quantum into TLS, or is it just how TLS
So
as it currently stands also works?
So yeah. So this is how TLS works. This is how TLS works using public key crypto. And if you want to move to if you want to move to quantum safe, the task is now to replace because today we are using schemes like RSA or elliptic curve Diffie-Hellman that are vulnerable against quantum computer. So if you want to have quantum safety as TLS, you need to replace those schemes with post quantum schemes. So after
please go ahead.
after the key in the key exchange, the goal is to generate something that is long enough to be quantum safe, because it is also known that for symmetric keys, we need to double the key length. So in most quantum safe TLS, usually we generate keys with bit length 256 instead of 128 has.
Okay. So there are multiple points of potential failure in TLS and the way the communication protocols are designed right now. So the only thing you really need to do is you don't need to change the underlying algorithm for how that is generated, let's say, but you only need to extend it so that it's a bit
Exactly.
longer, is my understanding. Okay. And
Exactly.
then what other parts of the communication procedure that you described are the ones that are currently vulnerable to attacks in a post-quantum setting?
So the vulnerable part are basically those. I mentioned the key exchange and
Yep.
the authentication.
Uh-huh.
So today we use RSA,
Mm-hmm.
RSA signature of authentication, or elliptic curve digital signature algorithm for
Mm-hmm.
authentication. For the key exchange, we use elliptic curve Diffie-Hellman, and those schemes are vulnerable to quantum computing.
Mm-hmm.
So
Okay.
in the quantum-safe TLS, we replace those schemes with one of the key encapsulation schemes selected uh, is Kyber,
Uh-huh.
and for signature we have Dilithium, we have Sphinx Plus, and we have Falcon. So
Okay.
Dilithium, Falcon are lattice based. Sphinx Plus is hash based.
How much of a consensus is there for those? So the four algorithms or the four algorithms or schemes that you just described now, are those the one-to-one equivalents of the NIST selected ones, or are we talking about different? Are there different naming conventions depending on how precise you are in the
Yeah,
application?
yeah. These are the name that the inventors gave to the schemes.
But we are
Um,
talking about, so the four schemes that you described just now, they are the same four schemes that NIST
yeah,
has
yeah,
approved? Yeah,
exactly, yeah,
okay,
yeah.
okay.
So
Uh huh.
Kyber, Dilithium. These are the name Kyber, Dilithium, Falcon, and so on. These are the names that the inventor gave to their schemes. But
Yeah.
NIST will use acronym. So I don't have that in the top of my head. So it's like advanced encryption standard AES was the standardization name that NIST chosen for Rinchdale. So the
Uh
initial
huh.
name of the algorithm was Rinchdale,
Mm-hmm.
and the standardization name is then AES. So for Kyber, Dilithium, Falcon, and so on, NIST will choose. So I think in the draft, in the standard draft, they already have standardization name, but I don't have that in the top of my head.
Mm-hmm. Okay. The next question I would have is we're saying that we're now replacing the authentication stage and the key exchange by means of these updated
Schemes, yeah,
schemes.
yeah,
Yes. Um, to me, those are both conducted at the, let's say, onset of a session. So it seems to me like we would not have additional overhead because part of the paper is assessing the overhead that comes as a
yeah.
consequence of implementing these. And it seems to me that the only overhead that you're incurring with that is an overhead in the establishing of a connection between the parties. Is that correct? Or do we also expect that in adopting these new schemes that you would have overhead on the actual communication time once you've established a connection?
So I think it depends. So in the paper we evaluated in two settings, so in LAN setting and in one setting,
Mm-hmm.
wide area network and local area network.
Yeah.
Um, so in the local area network, the running time was comparable to current schemes, and sometimes
Mm-hmm.
even much more faster.
Mm-hmm. I mean,
But this,
if you want to, we could even jump to the results now and have a look at
yeah, sure,
the
sure,
figures that you have,
sure.
because I mean, we have those in the paper. So let me just let's see. Do you have one in particular that you would like to start with in terms of just describing?
I think this one, for example, is in the LAN setting, and here we are using RSA for signature. We are comparing RSA and Dilithium as
Mm-hmm.
signature, and elliptic curve Diffie-Hellman and Kuiper. So
Mm-hmm.
here you can see that the running time for post quantum is much more better. The post quantum is much more faster. this is also the case when you use instead of RSA you use elliptic curve um, elliptic curve digital signature algorithm. So I think this should be the scheme, the figure below. This should be figure. Exactly. So in this case, we are using the SA elliptic curve and instead of RSA. So um, here you have similar result that post quantum is much more faster. But now,
Okay, how do we see? Very naive question, but how do we see that from this figure? So, which one are we comparing to as our baseline for standard procedure? Let's say.
So it's a little bit small. So for example, moving from the left. So we have the
Yeah.
no TLS. No TLS is we are doing the communication without encryption. And exactly, and then the prime 256. This is
Right.
quantum. This is pre-quantum, so quantum weak
Okay.
schemes, and dilithium and kyber are quantum safe.
Okay.
So
So the baseline on all of these figures, I suppose, is always on the left hand side. So this is the
exactly, yeah,
pre-quantum.
yeah,
Okay. Okay. Very
yeah.
good. So, how come? How come you're saying that the post-quantum is then faster? So looking at these ones, I would assume that elapsed time is sort of
So yes,
yeah.
yeah. On the row below, we have the security level. We have different security level. So we are comparing them at the same security level. So if you have in the first column of the last row, we have security level 1, and here you have comparable performance. But if you move to the next security level, you see that post quantum is faster. So this is
Okay. Okay.
this means that the running time here is smaller than using quantum weak schemes.
How come that's the case? So to me, that seems very counterintuitive. We have some structure now where
Yeah,
we've reached the state where we're not quantum secure. Nevertheless,
yeah,
it seems like the quantum safe algorithms then are more efficient than the current ones, even though they're also more secure. So are we simply saying that the algorithms that we've tested this with now are just performing at a higher level than the previous ones that we had, and we sort of made an improvement in all respects when it comes to these algorithms, or is there some price that we're paying for these post crypto or post quantum algorithms? Sorry, that we don't see in these graphs.
yeah. So one thing is that those schemes are using different mathematical structures. So for example, in RSA use is based on the prime factorization of very large numbers. So
Yeah.
for the case of RSA, you have to deal with very large numbers. Um, in the latest case, you have many numbers but smaller numbers, much more smaller. So this means that you can do the operation much more faster. So the price that we are paying is that we have much more larger ciphertext or keys or signature. So the
Okay.
communication size for post quantum is much more larger. And
What are the drawbacks of having a very large communication size there? Is it just
um,
let's say RAM requirements and these kind of things, or is it something else as well?
yeah, around requirement as well. But in many internet protocols, they have packet size. So they have packet size
Yeah.
for communicating between the protocols. And if the message is too long, you have to send. You will need more round trip to send the entire message. So the drawback is that if you move now in the figure in the one setting, you will see that post quantum is no longer faster.
Okay.
And
Okay. So
yeah,
right. So this is the LAN setting.
this is the
Sorry.
LAN setting. This is also the
Yeah.
LAN setting. The one setting I think is in the appendix. You have to scroll down to the last 2 pages or something.
Okay. You're
Yeah,
talking about
here.
these ones? Yeah.
Exactly. Yeah. So here we have the same figure as above. I think the same figure as figure 7 for the RSA case, and below we have a figure for ECDSA. So here you see that the situation is a little bit for RSA, post quantum is still a little bit faster, but not more no more much more faster than in the land case. And if you move to the elliptic curve case, you will see that at higher security level, elliptic curve is even faster. So my assumption here is because of the large communication, the communication we have it, the result of the communication we have it in figure 10. Because of the large communications, the protocol needs more rounds of communication, and this has impact on the final running time.
Right. Okay. So you clog the networks essentially more with the updated
Exactly.
schemes. That's the main
Yeah.
drawback. Okay.
Exactly.
When we're talking about the evaluation time here or the elapsed time, what exactly are we referring to now? Are we referring to establishing a connection and the time it takes for you to do the, let's say, handshake? I'm not sure if that's the appropriate term in this
Exactly.
setting,
Yes.
but
Yeah. Yeah.
okay. So this
So,
does not have anything to do with the communication that, let's say, is initiated after you've established the connection.
no. Also here we are measuring only the handshake. So the client start the connection.
Yeah.
From the point that the client start the connection until the point that they have agreed on common symmetric key.
Uh huh.
Yeah,
Okay.
because
And
after that they will use the same key to encrypt the communication using AES. So we also have a figure for that. Um, I think it's one
is it further
figure
below?
above. No, I think it's one figure above.
Okay.
It's in the main body. So yeah, I think it is this one. No. This one is for the communication. So um, here we are comparing the communication between with the case when you use only quantum weak scheme and quantum strong schemes. So
Okay.
if you uh, and we are also comparing, I think, different security levels. So I think from bottom to top, we have quantum weak, and then you have quantum safe. You see that the bar of dilithium and kyber is much more larger than the 2 bars below.
Yes.
And exactly. So the communication is at least two to three times larger than in the quantum weak case.
Okay. And this is for also establishing the handshake or for the actual
This
communication
is
then?
this is this is only for the handshake.
Okay.
Yeah,
Okay.
yeah. This is
And when it
this
comes,
only for the yeah.
okay.
So
Okay. So
on the picture below we have I think it is figure yeah,
this
this
one?
one. So here we measure I think that is the time it's needed to encrypt 100 megabyte of data using the agreed symmetric keys.
Uh huh. Okay.
Exactly.
And do you know how this scales over with the amount of data being, or let's say maybe it's not the data that's so relevant. I guess the most relevant metric is how many rounds of communication you have, right? So so you have plenty of figures on establishing the handshake, and it's
Yeah,
clear like that. It seems the algorithms that are quantum safe are actually faster than the existing schemes or the currently implemented schemes, but the price you pay is the key length and the bandwidth of the communication.
exactly. Yeah, yeah.
And what I'm trying to get to with this is, fine, we accept some form of drawback in the initiation process, and maybe we can deal with that because it's a one-time process whenever we establish the communication. But let's say that we have a significantly longer key length that we transport with every message of communication. Potentially, then we also have significant penalty in the communication after we've established a connection. Is there any do you know what the asymptotic difference is? Like, how, if you have, let's say, an infinite communication length, like let's say you're
Yeah.
communicating with an infinite amount of messages, how much more expensive would it be with the quantum safe algorithms compared to the existing schemes in that
No,
limit? Do you have a
no,
view
no.
on that?
Basically, there is no difference. So the only difference is because the communication is encrypted using asymmetric encryption,
Yeah.
and the ciphertext has basically the same size as the plaintext because because you use here block encryption, and you divide your message into blocks. For example, if you're using IS, you have block of 128. So you will divide your message in block of 128 bits. The only difference is that for the last block, you might have less than 128 bit, and you have to pad such that the length is also 128 bits. So basically, the size of the plaintext is the same as the ciphertext. But you will from the bandwidth perspective, the overhead is negligible.
Okay.
From the running time, you will need to take care of having IS as fast as possible.
Uh-huh. Okay, understood. So, given that we have the information now about how much more bandwidth is required, roughly speaking,
Yeah.
with the quantum safe encryption schemes compared to the classical ones, if we keep that in the back of our heads and then we think about how significant of a concern it is with establishing these communications to begin with at the moment, is establishing a communication with the existing protocols a significant, let's say, a significant like overhead on the system compared to general communication, or is that sort of negligible in the larger scheme of things? How much of the resources do we currently allocate? Let's say if we're analyzing networks in general, how much of that is allocated to the actual establishing of a connection compared to the communication back and forth once that's been established? Do you have a view on that?
So for the resources that you need, so you will need at least enough RAM to store all this communication. So this means that because the communication is much more larger, you will need more RAM,
Yeah.
for post quantum to store to do this calculation, because you need um, uh, to um, you need to run the algorithm in the memory and so on. Because of the key length, you need to load the key in the memory, a much more larger key in the memory, and so on. So this will, for example, if you have small devices with very small RAMs, you will have a problem with this kind of protocol, with quantum safe schemes. So
Okay, so that's clear. In terms of if you're comparing establishing these connections, there is a significant more or larger requirement. On a very high level point of view, like if I
yeah.
ask a very naive question, perhaps, given what these infrastructures deal with at the moment, is this increase in bandwidth significant, taking everything into account? Like it is if we only consider the point I'm trying to get to is
Yeah.
this increase here is significant if we only look at what it took to establish a connection before and compare that to what it takes to establish a connection now. But
Yeah.
maybe establishing a connection with these schemes is not really a big piece of the cake, let's say, in terms of what these network structures have to deal with. So from your perspective, talking about network requirements or device requirements in general, is this a significant, like, would
Yeah,
this effect have a significant impact, do you think?
yeah, I think this is already significant. So um I think this is already significant because for small device connecting to a web server, it means that we'll be downloading much more data as nowadays. So
Uh-huh.
this already has significant impact.
Mm-hmm.
So I think we need to find some way to optimize this, maybe by um, one of the possibility is to preload the certificate of the is to pre-share the certificate of the server instead of sending it every time in the during the communication. This might reduce the bandwidth a little bit. There is also a new scheme called Chem TLS, where they use key encapsulation uh, to do where they use much more key encapsulation. So they reduce the number of signatures in their schemes, and this also has impact on the final communication. So they can reduce the communication by reducing uh, the number of signature and using key encapsulation instead.
Uh-huh.
Yeah.
Okay. Okay. I think in terms of next steps, if we think about just reducing this bandwidth, is there anything else that you think, like, that you would be optimistic could be done to reduce this, or are those the ideas that you have regarding how we could proceed with that?
Yeah, I think these are the two ideas that I see right now. So I don't
Uh-huh.
know. Yeah, I think these are the two that I'm aware of. Yeah.
Okay. Okay. Cool.
So
That.
basically, when you there is a certificate chains that the server send to the client. So one possibility will be to reduce the length of the chains such that less certificate are sent during the communication. So the certificate
Mhm.
are preloaded, are already pre-shared on the client. But this, of course, will not work for all applications.
Mhm.
Because also pre-sharing all the certificate means that you need enough storage to store them.
Mhm.
Yeah,
Okay.
this
If
will
we
not
think
work
about
for any use case. Yeah.
Uh-huh. If we think even more fundamentally about the architectures that we have associated with this now, and I'm showing the architecture for the particular implementation of the paper here, is there anything that could be done in terms of how these are structured, do you think? Like, granted, this is, well, you also have the implementation of the quantum safe algorithms here, or the quantum safe schemes here. But thinking about this from an even more higher level of abstraction, do you
Mhm.
think there are other kinds of architectures that would be better suited for these kinds of post-quantum algorithms as opposed to the ones that we already established? Because this client-server architecture, for example, that all of this is based around, if we look at it from the lens of having that as a given, then
Mhm.
sure, maybe those are the only ways forward. Do you think there's any, yeah, are you optimistic about having changes in the architecture that better utilize post-quantum algorithms?
Yeah, that's a very tough questions. That will require more research. But I think what is still possible so I think it's still possible to optimize the architecture and the implementation such that the runtime is the runtime gets better.
Mm-hmm.
Um, but for the communication, I don't see anything. I don't see any solution besides what I mentioned before. So because we cannot optimize the size of the public key or the size of the ciphertext. These are given. These are parameters that are given that we cannot change them.
Yeah.
But we can still do the implementation in such a way that maybe using hardware accelerators, such that the running time of generating the signature or encrypting is much more faster. This is still possible using hardware or using uh, optimized implementations. But for the for the bandwidth, yeah, I don't see how I don't see how you can optimize this beside the two options I mentioned before. So either reducing the chain the certificate chain length, or maybe using chem-TLS. But this is still
Okay.
a research that we need to do to have confirmation.
Understood. Yeah. If we think about the wider space again, and just looking ahead in the space of post-quantum cryptography in general, is there
Yeah.
anything that you would like to see from like the research community in that area or from industry in that area as well that is not being addressed at the moment? Like it, as far as you see it, what are the big hurdles for us implementing this kind of technology at the moment?
Can you repeat the last sentence again, please?
Yes, so I'm just asking what kind of hurdles you see with the implementation of these post quantum cryptographic protocols that are not addressed at the moment that you think either the industry or academia should focus on trying to solve? Like, are there
Yeah,
any things that you see going forward, thinking about future research and future implementations that we should focus on addressing collectively that are big unsolved problems that we still need to focus on?
yeah, there are still a lot of things that that need to be done. So um,
The
it
ones,
takes
yeah,
time.
the ones that are
Yeah,
close to heart in that case, like the ones that are most closely onto the field of research that you're
yeah.
heavily involved in. Yeah.
First, it takes time to get confidence that that the scheme is secure. So we still need um, to uh, to investigate those schemes. So we cannot be confident after only a few years that the schemes are secure. And there are a lot of things a lot of things that need to be addressed, like side channel attacks. So this is ongoing research uh, uh, on post quantum schemes. So to investigate the impact on side channel analysis. So because you can have a scheme that is secure, but from the implementation, it's still possible to uh, uh, um, to recover the private key, for example. Um, um, and then you have things like basically the key exchange that we use today, the Fierman, is non-interactive. So key exchange means that I send you a message, then you send me a message, and from the message that we send to each other, we can derive a common semantic key. Um, in the case of Diffie-Hellman, we can send each other the message at the same time. So we don't need to do it sequentially. But all the key exchange, all the key encapsulation, all the post quantum key encapsulation are interactive. So I first need to send you a message, and from that message you can send me another message that I can use to derive the same key as you. So there is the concept of non-interactive key exchange that are useful for other applications that we don't have yet uh, in post quantum schemes. And also, most of the I mentioned before already that uh, there's the problem of the size of the size of the ciphertext of the keys and so on.
Yeah.
which uh, this is the problem because with that we don't have schemes that can be used for all use cases. Kyber and Dilithium are better for TLS, for example, for the internet, but they might not be good for load devices, for example. There are
What's the reason
schemes.
for that? So, would you mind just elaborating a little bit further on why we have that dichotomy? Like, what is the reason for them being more suitable to internet, for example?
Though the reason is, for example, based on the investigation that we done, or based on the investigation that other people did. So using Kyber and Dilithium to implement TLS. So after those investigation, those investigations show that the overhead is acceptable.
Mm-hmm.
But this is on the assumption that we are using a large enough client to do this communication. So if the client is a small device, then I don't know, it's a smartwatch or something like that. It might be different.
Uh-huh.
So, and then you have schemes, post-quantum schemes, so-called stateful hash-based signatures. So basically, they have a kind of state which is part of the private key, and this requires that after generating a signature, you need to update the state. So basically, update the private key.
Mm-hmm.
And these are the kind of schemes that are not suitable for the internet, for example, but might be suitable for software updates. So if I am a software provider and I want to ensure my customer that that their software package are legitimate, I use digital signature to certify it,
Mm-hmm.
to ensure that. For this kind of use case, you can use stateful hash-based signature. So basically, so there are no schemes that are suitable for many use cases at the same time, and this is one of the reasons that NIST started a new call, I think last year, for for new signatures, with the goal to have signature that can be used for many use cases at the same time.
Uh-huh.
So yeah.
Okay. Okay, great. Before we wrap up, is there anything else you would like to like say regarding the state of these technologies, or the research that you've done? If there were any points I didn't cover, anything that you would like to just mention before we close?
Something that is very important and that many people talk about is the concept of crypto agility. Um, with post-quantum schemes, crypto agility become much more important because as I said before, we need time to ensure the confidence of the scheme. So this means
Mm-hmm.
that we can move to post-quantum schemes, and few weeks later, scheme are broken. So we
Right.
need kind of we need a new kind of possibilities to change schemes as quick as possible without disrupting running system. So this
Mm-hmm.
is a concept of crypto agility that is still to be defined. That people are looking how to how it will look like in the state of post quantum security.
Right.
So I think, this is and I think most of the experts are recommending to start working with post quantum security now. So we don't have to wait that standardization already, or that we have cryptographic relevant quantum computer. we can already start now assessing those schemes, trying to integrate them into system to be ready when the standard will be ready as well. Because it takes time. It takes time to integrate new cryptography or to replace broken cryptography in existing system. So there are a lot of resources on the internet from the NIST webpage and also I think in the paper as well that can point to that.
Okay. Okay. Awesome. Well then, thank you very much for taking the time. I appreciate the discussion. I had a lot of fun. So thanks for giving the overview.